Good morning, good evening, good afternoon, whenever it is you're watching. Thank you for watching. Today we're going to be covering section 6.3, periodic law. Okay, periodic law. I'm working with fifth period again. They're a really great group, and they don't mind being recorded, right, guys? You guys don't mind? You guys don't mind? All right. So thank you. Don't worry, you guys. They don't see. They don't see you guys. They don't see your. They can only hear you guys. Okay. Hold on. I'm fixing something. Okay. All right. So I need a volunteer to help me introduce today's topic. How are these items related to one another? And you have a candlestick, you have some rope, you have a letter opener, you have a gun, and then I don't know, you got some tools in there. I don't know what they're for. Who's going to read? Oscar?
Yeah, we have all enjoyed playing the game Clue. The object of the game is to obtain information about a murder. Who did it? Where they did it, and what was used as a murder weapon. As the game progresses, clues are obtained by each player, and they then must assemble these clues into a guess as to the criminal. Individual pieces of information take on broader significance when put together with the other parts of the puzzle.
Thank you, Oscar. Okay, so has anybody here ever played Clue, the board game? Has anybody ever played Clue? Irvin, you've never played Clue?
I think I have.
You've played it?
Yeah.
You guys have played it? Okay, so how does it work? How you go around and you pick a card, no, or something like that? I've never played it myself, but my understanding. Go ahead.
Yeah, I think it's like that. Like it's like you just get a card and it's just like different rooms, and you go check like.
Right. Like, okay, as far as what I understand about Clue, Oscar, is that there's different rooms in a make believe house, right? And there are different people in the room, and then somebody always ends up dead, right? And so you're going to be getting, so each player, as the game goes on, everybody will be getting these cards, these clues about the murder, right? And some cards will say this person was in the library with another person, right? Like the butler is in the library with the maid, and then it'll say the cook was in the kitchen with the valet, with the valet, which is like the person who does the driving, the driver. And then, everybody has different clues. Like I will get a clue, that Oscar will get a clue, and then another person will get a clue. And eventually I think you share the clues. Do you share the clues? Is that what happens, Oscar?
I haven't played it. I played when I was like super small.
Oh, okay. Well, what I remember is that you start to share your clues with the other players. And as you're sharing the clues, you're able to figure out, okay, well, this person wasn't in the room that the person died in. So he's out. Like the cook is not the person, is not the murderer, because he was in the kitchen working with the maid. And so the maid and the cook are not our criminal. And then and then it gives you more and more clues so that you're able to figure it out and guess who the person was that committed the murder and how they did it, right? They always say it was John in the drawing room with the candlestick, or it was, and it'll give different names, and it will say it was this person and they used a rope to kill them, or it was this person and they had a gun to kill them. Okay. But what the point of why we're talking about Clue is because when Mendeleev published his periodic table, he was missing certain vital, very important information that would lead to a better periodic table, these different clues, right? So that's how come we're talking about it as the introduction, because it does relate to information that Mendeleev didn't have. All right, these clues were discovered later, later in time, and so another person was able to use Mendeleev's periodic table and this new information, these new clues, to create the periodic table we have today. And they kind of referred to it as periodic law. All right, so let's talk, or let's read. When Mendeleev was publishing and putting his periodic table together, he didn't know about the existence of the nucleus. Why? Because the nucleus wasn't discovered in 1869. It wasn't discovered until maybe 30 years later in 1911, when Ernest Rutherford was conducting his gold foil experiment. And when he did this gold foil experiment, that's when that nucleus was finally discovered. Okay? Now let me tell you a little bit about the gold foil experiment, about Rutherford's experiment. So everybody knows aluminum foil, right? Aluminum foil is very thin. It's used for cooking most of the time. But you could also use it for experiments. And Rutherford was using it for his experiment, except it wasn't aluminum foil, it was gold foil. And so he put up the gold foil and he started shooting these little alpha particles. Okay, think of them as like beams of light. And these alpha particles are positively charged, and most of them were going straight through, right? They were going straight through the paper. And most of them went straight through because it wasn't hitting anything, right? When it comes to atoms, it's a lot of empty space in between. Every 1 in 1,000 or 100, or I don't even remember what the number was, but there was a couple of those alpha particles that would bounce back and bounce to the side. So he said, okay, well, I know that most of these particles are going through, very few are bouncing back. I know alpha particles are positively charged. So if there was something in this gold foil that was negatively charged, those alpha particles would stick. In the case of his experiment, these alpha particles were bouncing back. They would hit, they would bounce back, hit, bounce back. And it was only very few of them. So he said, there's got to be something in that gold foil that has a positive charge. And he named it the nucleus. And that's all we knew at the time. All we knew is that there were, in these atoms, there was a nucleus that had some type of positive charge, but we didn't know why. Okay? And we didn't know why for about 2 years. 2 years later, in 1913, English physicist Henry Moseley is conducting his own research. And he was researching, or he was examining the X ray spectra of a number of chemical elements. And he would shoot X rays through crystals of the element and study the wavelength of the radiation he detected. So X-rays, right? You take a picture, basically you're sending energy into, in this case, a person, right? If you're taking an X-ray of me, well, you're taking an X-ray of my arm probably because we think it's broken, right? So you take a picture, energy flows through, and you're able to see where, in fact, my bone is broken. Now, in this case, he was taking a picture and he was shooting X-rays of different chemical elements, and as the light passed through, it would give off a certain amount of energy, right? And that energy, that's what he was studying. He was studying the wavelength of energy, right? Because energy, just like the energy that's coming out from my light, it's not coming out in straight lines. It comes out in curves, in waves. Okay, I don't know if you knew that, but it's a little bit of physics. And so these waves, this beam of light, can be measured, and you can measure how long that wavelength is. And as he was doing his research, excuse me, Moseley found that there was a relationship, there was a connection between wavelength and the atomic number of each element. Now, his results led to the definition of atomic number as being the number of protons contained in the nucleus. Okay, it contained the nucleus. So, what ended up happening? What was the results after that? He realized that if elements on the periodic table, they shouldn't be arranged according to increasing atomic mass. It's better if it's by atomic number. An atomic number, always remember, is the number of protons. So for hydrogen, if you look here on the periodic table that we have here, hydrogen has an atomic number of 1. So that means in that nucleus for hydrogen, you have 1 proton. For boron, the atomic number is 5. So it's going to have 5 protons in the nucleus. For oxygen, it'll have 8 protons. For fluorine, 9, and so on and so on and so on. Okay? Now, why? Why did he reorder the periodic table by atomic number? Well, there was a couple of problems with Mendeleev's periodic table. When he changed it from atomic mass to increasing atomic number, it fixed those little discrepancies, those little problems, excuse me, that Mendeleev periodic table had. And one of those problems that we're talking about was the iodine. Remember he had to switch iodine and tellurium because iodine reacts very similar to bromine and chlorine and fluorine. So he switched these 2 elements, tellurium and iodine. Now, tellurium has an atomic number of 52, while iodine has an atomic number of 53. Okay, so if you were to look at a periodic table that has all the information, and let's check it out real quick. Let's look at this periodic table right here. If you remember, and right here, iodine. Iodine has an atomic mass of 126. Tellurium has 127. So when it came to Mendeleev's periodic table, it should have been iodine first and then tellurium. But Mendeleev switched it. He switched it because iodine reacts like the other elements in this group, bromine, chlorine, and fluorine. Now, when it came to Moseley, Moseley was able to find the atomic number of iodine, and it was 53. For tellurium, it was 52. So that was it. That gave us a reason why to put tellurium before iodine. Okay? That gave us a reason why we had iodine after tellurium. So even though tellurium has a bigger atomic mass than iodine, it is properly placed before iodine because of the atomic number. Mendeleev and Moseley are credited for being the most responsible for what's known as modern periodic law. And what is periodic law? Well, the definition is right here. When elements are arranged in order of increasing atomic number, there is a periodic repetition, meaning that there is a pattern that repeats. And what it repeats? Those chemical and physical properties. The result is the periodic table as we know it today. We still have that periodic table. It hasn't changed since 1913. Now, and they start to give us examples of these chemical and physical properties that repeat for each horizontal row. So we're talking about across, right? These periods. They're called periods, right? You got 1 through 7. So each new period, it says here, each horizontal row of the periodic table represents the beginning of a new period. And or why? Because it starts a new energy level that's being filled with electrons. Okay, so this energy level number 1 has a certain number of electrons, and then you have a new energy level known as period 2, a new energy level in period 3, 4, 5, 6, and 7, and so on. Okay, so that's one of those repeating patterns that we have. Another reason elements with similar chemical properties appear at regular intervals within a group or a vertical column. So here, if we're talking about this red column that you see here, this is a group. How many groups are there? 18 groups. This first group is called the alkali metals. All of these, from lithium all the way to francium, all react the same. Group 2, alkali earth metals, it's the same thing. From beryllium to radium, all of them act the same. The same thing happens with group 18, the noble gases, they all act the same. For group 17, the halogens, they all act the same. Okay, and there's a lot more groups that we'll talk about later when we get into that. All right, let's check out this video real quick.
All right, so in this video, I'm going to talk about periodic law. So what do I mean when I say periodic law? I'm just talking about, the origin of our modern periodic table. So the empirical laws by which our modern periodic table is based. And I think a good starting point for the discussion of periodic law is with the early periodic table that was proposed by a Russian chemistry professor named Dmitry Mendeleev. And in Dmitry Mendeleev's time, there were 65 known elements. So not many of the elements that are known today were known back then, but the properties of many of these elements were known. So what Dmitry Mendeleev did was he arranged the elements, the known elements, in order of increasing atomic mass. And when he arranged these elements in order of increasing atomic mass, he found that certain properties reappeared periodically.
So he's going back.
Just to give you an idea of what.
So he's going back to what we talked about yesterday about Mendeleev and the early periodic table that only had 65. When Mendeleev put that periodic table together, he ordered it in increasing atomic mass. And why? Because there was repeating patterns in the chemical properties of these 65 elements. And he's going to tell you about an example right now.
What that means. Here I have a list of the first 12 elements on the periodic table. So hydrogen is the first one, helium is the second one. These are arranged in order of increasing atomic mass. So like I said earlier, the properties of all these elements were known. So it was found that hydrogen and fluorine had similar properties. Helium and neon had some of the same properties. Lithium and sodium had some of the same properties. And beryllium and magnesium also had similar properties. So notice we have what.
So right now he's trying to show you an example of these repeating patterns within the elements that Mendeleev was talking about.
Looks like sort of a pattern. We have this red, green, yellow, blue, and then 4 elements, and then red, green, yellow, blue, and then maybe there are 4 other elements like these 4, and then perhaps we'll get our red, green, yellow, blue pattern again. And indeed, you do. If you were to continue this list in order of increasing atomic mass, you would see this pattern recur. So that was what the early periodic table was based on. So he took what he did was he took this data and he arranged just a simple table. So let's say that's my table. And this table has rows and it has columns. Put some more rows in there. So in each row, from left to right, the atomic mass was increasing. And the rows were arranged in such a way as that the columns would have elements that all had similar properties. And this is also, in a nutshell, what our periodic table today is based off of. However, there are a few differences. So, for the modern periodic table, well, first of all, instead of 65 elements, we now know of 119 of them. And another difference is that the elements are actually arranged not in order of increasing atomic mass, but in order of increasing atomic number, or the number of protons in the nucleus. So if you consult your periodic table and you look up a column of the periodic table, those elements that make up that column are going to have some of the same properties. That's basically...
All right. So the reason why he brought that up is because this is what we have today. Today's periodic table follows Moseley's version. Why? Because instead of it being by atomic mass like Mendeleev, we have changed it to follow Moseley's periodic table, which was ordered by increasing atomic number, and it was able to fix some of those little problems that Mendeleev's periodic table had. It still follows Mendeleev's version because there are still groups. There are still groups of these elements together according to the way that they react, because those chemical properties have a tendency to repeat. All right. So thank you, sir, for helping us out with that. So in conclusion, let's summarize today's topic. Elements of the periodic table are arranged in order of increasing atomic number, thanks to Mr. Henry Moseley. Periodic law states that when elements are arranged in order of increasing atomic number, which is Moseley, there is a periodic repetition of their chemical and physical properties. That was from Mendeleev. So they smashed both of those scientists together, and they came up with this periodic law. So I'm going to give you a couple of minutes. I'm going to give you about a couple minutes because I need like 2 or 3 minutes. Let me finish doing attendance, and then we're going to discuss. You know what? I'll give you, because it only takes us about 10 minutes to discuss the answers. So I'll give you about 6 minutes to start trying to do these questions. Okay? You are to try. I know you might not be able to finish all of them, but you should be able to do some of these questions, okay? And remember, you are doing it in, you should be using this one right here, the one that says Wednesday, October the 21st. It's called Review Question 6.3 and 6.4. That's the one I want you to use to answer the questions, okay? Try to do as many as you can, Don't worry if you don't get to do all of them. We're going to come back and talk about them. All right. Any questions? I need to work on attendance. All right.